Hi everyone, welcome to the Arithmetic Zone. Here we have a video for you guys on implicit differentiation, which is a technique used in many calculus courses, and it's a really important one when you proceed onto higher level math. So let's get started. So what is implicit differentiation? Well, it's used when you want to take the derivative of a function or equation that is either difficult or impossible to express in terms of a single variable. So what do I mean by that? When I say a single variable, let's take this example, y is equal to x squared. This equation is expressed in terms of a single variable y. So when taking the derivative of an equation like this, we want to think of a derivative as if it were an arithmetic operator, such as addition or subtraction. So we're going to take the derivative here. This is going to be our derivative operator d dx because we're taking this derivative with respect to x. We're going to do it to both sides. Well, the derivative of y is just going to be dy dx, the derivative of y with respect to x. The derivative of x squared is 2x, and the derivative of x with respect to x is going to just be tacked onto that. Now, dx dx is really just 1. We're going to just label that as 1. So we're going to have dy dx is equal to 2x. Now, that should have been simple enough because y equals x squared is a very basic, common equation. It's a parabola, and it's one of the most fundamental derivatives that we have. But we're going to look at some trickier examples where this implicit differentiation technique is going to come in handy. So now let's find the derivative of the following equation with respect to x. This is y squared is equal to 3x to the fifth minus 7x. So you could take the square root of both sides and have it in terms of one variable being y is equal to the square root of 3x to the fifth minus 7x. But I feel if you go through the process of taking the derivative of both sides from the beginning, it's a more intuitive process, and in the end, it'll be easier to solve. So let's do that. Let's take the derivative of this whole equation. So now we have 2y times the derivative of y with respect to x is equal to, well, the derivative of 3x to the fifth power is 15x to the fourth times the derivative of x with respect to x minus, well, the derivative of negative 7x is negative 7 times the derivative of x with respect to x. So we've already established that this is 1. dx dx is 1. So now we have 2y dy dx is equal to 15x to the fourth minus 7. And now our goal is to isolate dy dx. That's what finding the derivative entails. So we're going to divide both sides of this equation by 2y to get our final answer of dy dx is equal to 15x to the fourth minus 7 over 2y. It's in terms of x and y because we found the derivative implicitly, whereas when we found it explicitly here, it was only in terms of x. So now let's look at another practice problem. We're going to find the derivative with respect to x of the following equation, x squared plus 16xy plus y squared is equal to 1. So let's go ahead and take the derivative of x squared, which is 2x, plus 16xy. So 16xy, we have two different variables being multiplied together. So this is going to actually be a product. We're going to take the derivative of the first term, 16x, which is just 16, and then multiply the y, plus the normal first term, 16x, times the derivative of the second term, dy dx. And then we're going to move on. The derivative of y squared is going to be 2y dy dx is equal to 1. Now you may be wondering why when we took the derivative of x squared, I just left it as 2x and I didn't add the dx dx. And same thing when taking the derivative of 16x, I just left it as 16 and not dx dx. It's because we've already established before that dx dx is just equal to 1 and multiplying any number by 1 is itself. So in order to save space and time, I'm just not going to write it from this point forward. So now we can go ahead with simplifying this. Oh, my mistake, the derivative of 1 is not 1, the derivative of 1 is 0. So let's go ahead and simplify this. We have 2x plus 16y plus 16x dy dx plus 2y dy dx is equal to 0. So now we want to isolate dy dx, so we're going to move every term that does not have a dy dx attached to it to the other side. So we're going to have 16x dy dx plus 2y dy dx is equal to negative 2x minus 16y. I just moved these terms to this side of the equation. And so now, in order to further isolate dy dx, we're going to factor it out. So we're going to have dy dx times 16x plus 2y is equal to negative 2x minus 16y. And now we're going to divide both sides by 16x plus 2y to get dy dx is equal to negative 2x minus 16y all over 16x plus 2y. And if you want to further simplify, we can take out a 2 on both sides. So we take out the 2 with negative x minus 8y over 2 times 8x plus y. The 2's will cancel out, and we're left with negative x plus 8y over 8x plus y. Sorry there. Just going to rewrite this. Negative x minus 8y. And so that's our final answer. You can leave it unsimplified as long as you go through the process of showing what you did. It should be fine. Well, I guess in reference to the AP Calculus course, if you're taking a college calc, you might have to check with your professor. So let's move on to, let's move on to our next example. Here, we're asked to find the second derivative of the following equation with respect to x. So we're going to go through the same process of finding the first derivative, and then once we have that, we're going to see what we do to find the second derivative. So let's get started. We have x squared, the derivative of that is 2x. The derivative of 4y squared is going to be 8y dy dx. And the derivative of any constant is 0. Let's isolate for dy dx. This should be fairly simple. 8y dy dx is equal to negative 2x. We're just going to move that right along. And then dy dx is equal to negative 2x over 8y. And then further simplifying that down, negative x over 4y. And I'm actually going to rewrite that here to show what we're going to do for the second derivative. Well, we're going to do the same thing that we did here. We took the derivative of this whole equation to get this differential, and we're going to do the same thing. We're going to take this whole thing and multiply it by ddx. So now we're going to have the second derivative of y with respect to x. This is our new notation. And now we're going to take the derivative of this right-hand side, and this is actually going to be a quotient rule. So the derivative of negative x is going to be negative 1 times the bottom, 4y, minus the top, negative x, times the derivative of the bottom, 4 dy dx, all over this denominator squared. So 4y squared. Now, we've already done the bulk of the calculus work, and now it's just algebra and arithmetic. So we're going to simplify it further. We're going to have negative 4y plus 4x dy dx over 16y squared. Now, I want us to notice something. We have this dy dx term here, and we don't want to leave it like that when we're expressing our second derivative. So we've already established that dy dx is equal to this term right here. So what we're going to do, we're just going to plop it right there for our dy dx. We're going to direct substitute. This is going to be equal to negative 4y plus 4x times negative x over 4y all over 16y squared. So just simplifying that down, we have negative 4y plus, or rather minus, sorry, there's a negative in there, minus 4x squared over 4y all over 16y squared. This is a very tedious problem just because, and this happens with most second derivatives. This is going to be x squared over y over 16y squared. Now we have a double-decker fraction. We have a fraction in the numerator and in the denominator. So I'm actually going to get common denominators with our numerator. I'm going to take this negative 4y term and put it over 1. And I'm going to multiply both the numerator and the denominator by y. So we have our second derivative is equal to negative 4y squared over y. Simplifying this down, we get negative 4y. We're not changing the value of anything, we're just making it more suitable to our simplification process. Minus x squared over y. This denominator stays the same, 16y squared. And now we can take the common denominators and rewrite it like this. Negative 4y squared minus x squared all over y divided by 16y squared. And then we can simplify this further to get negative 4y squared minus x squared over 16y cubed. We just took this term right here and multiplied it by y. That is a property of fractions that you should have learned in your algebra courses. And so this is our final answer right here. So that was a lot of work. Finding the second derivative is oftentimes very tedious and very algebra heavy. You just have to be very careful with what you plug in and all of those tricky or sneaky arithmetic operators. So now for our final practice problem, we're going to find the derivative of the following equation with respect to x, the first derivative, and then we're going to find the slope of the graph at the specified coordinate point. So a derivative is an instantaneous rate of change. So this is how we apply or we bridge the gap between our written derivative work here and how to express it on a graph. So now we're working with our sines and cosines. So we have to be familiar with our trig, our unit circle, and we do have series on that if you aren't too familiar with it. So this is going to be one that really tests our math knowledge. So without further ado, let's get started. So sine y squared. Well, the derivative of sine is cosine. Cosine of y squared, this is a chain rule. So we're going to multiply this by the derivative of y squared. So that would be 2y dy dx. So now we have a cosine of x squared term. The derivative of cosine is negative sine, but notice it's a negative cosine. So the two negatives will cancel out, and we're going to have a plus sine of x squared, and the derivative of x squared is 2x, is equal to cosine of y squared. The derivative of cosine is negative sine of y squared, and the derivative of y squared is 2y dy dx, plus the sine. The derivative of sine is cosine. X squared, our inside stays the same, times the derivative of x squared, which is 2x. Now we have to simplify. This is a lot. So first, let's just get our multiplication out of the way. We're going to have 2y dy dx cosine of y squared plus 2x sine of x squared is equal to negative 2y dy dx sine y squared plus 2x cosine x squared. It's really good if you like talk your way through this process or even just like parse it in your head so that you don't get too lost. And so now we want to isolate our dy dx's. We're going to get all of our dy dx terms on one side and everything else to the other. So my plan of attack here is to move this term with the dy dx over to the left-hand side and to move this term without the dy dx to the right. So we're going to keep this term unchanged. 2y dy dx cosine of y squared. Now we're going to add the 2y dy dx term over here, plus 2y dy dx sine y squared is equal to 2x cosine x squared minus 2x sine x squared. So I just want to check my work, see if we are on the right pace. And yeah, everything looks good. It's nice to take a step back and just see if all of your stuff is in order so that if you make a mistake later on, it's not as damaging. So we're going to take out that dy dx. We're going to factor it out. Dy dx times 2y cosine of y squared plus 2y sine of y squared. You cannot combine these terms because cosine and sine, they are different functions. You cannot combine them. They are not like variables. And then this is going to be all equal to 2x cosine x squared minus 2x sine x squared. We're going to divide this whole term over on both sides to get dy dx is equal to 2x cosine x squared minus 2x sine x squared all over 2y cosine y squared plus 2y sine y squared. That was a lot of work just to find the first derivative. We're not done with the question yet. And in fact, I'm going to actually simplify this further. We can take out a 2 from every single stage of this equation. There's a 2 term here, 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 and here in all 4 terms. So I'm just going to do us the liberty of taking that out now. So we're going to have x cosine of x squared minus x sine of x squared all over y cosine of y squared plus y sine of y squared. And to just give myself a bit of space, I'm going to erase all of this work that we did for the first derivative, but it is important. So I hope you guys understood that. It's just to make room for the second part of the problem. I'm just gonna erase all that and I'm going to move u up here. This is what we determined was our equation for dy dx. And so now we're going to evaluate this at the point root pi comma root pi. X and y happens to be the same coordinate point here. So our notation for this, I'm going to take dy dx, then we're going to have this vertical line at the point root pi comma root pi is equal to, now for every instance of x, I'm going to replace it with root pi, and for every instance of y, I'm also going to replace it with root pi. So I'm going to have root pi cosine of the square root of pi squared minus root pi sine of the square root of pi squared. You want to be really careful with your parentheses and your exponents so that you don't get mixed up. So please take your time if you are not comfortable with this kind of stuff. So now the denominator, we have root pi cosine of the square root of pi squared plus root pi sine of root pi squared. So we should notice that we have root pi as our common term in all 4 of these cases, so we can factor it out and cancel it. I'm not going to show that step because that is a lot of space, so we're just going to take cosine, and now root pi to the second power is just pi. It undoes that square root, and it's the same case for every single one of these terms. That's what's happening inside all of these cosine and sine functions. So we're going to have cosine of pi minus sine pi all over cosine of pi plus sine of pi. So if you do not remember, it is okay. Cosine of pi is going to be equal to -1. Sine of pi is 0. We're going to go down here again. Cosine of pi is -1. Sine pi is 0. We're going to have -1 minus 1, or -1 minus 0, all over -1 plus 0. So this just reduces to -1 over -1, which is simply 1. That is going to be the slope of the graph at that specified coordinate point. And we did that through the use of implicit differentiation. So those are the main use cases of implicit differentiation when you want to find the second derivative of a seemingly innocent looking function, but it actually turned out to be a lot worse. Or if there's just a bunch of x's and y's mishmangled into an equation. So that's going to be it for this video. But up next, we're going to have a challenge problem. I'm going to be honest, this challenge problem is a lot. Even just printing it out was hard to do, and it would be very unlikely for you to be expected to be able to solve it in a typical calculus course. But here it is. Can you find the derivative of this monstrous, nasty looking function? We're going to be going over this next week, and I hope to see you there. Thank you so much for watching.